Yeah. Or sorry, not Tuesday. It's next Monday. Thanks for spotting that. That's an immediate fix. I think I was thinking of my other class that has meets on Tuesday, Thursdays. Whoa. Close the hat.
What are you watching?
That was the same recording that we have, just feedback coming through, I think. Welcome back, folks. Looks like we could get started. Yeah, that little thing that screamed at us for a second was whenever I start the recording, it opens the actual YouTube channel. So I always try to click off that page as fast as possible. Just forgot this time. But welcome back. The Canvas page this time is just covered with announcements, but let's go through them one at a time. Quiz 5 is going to be due tomorrow. Some people probably have already worked on that one early, and this was based off section 5.4. That makes it a pretty pivotal quiz because what you are going to do on that quiz is extremely similar to what you're going to do on exam 2. On exam 2, I did put down sections 5.1, 5.2, 5.4 because those were the sections we covered, but I'm really going to focus more on a 5.2 style question. So work on that quiz. As soon as you get that sent in, I'll be working on grading on Friday. I'll get your feedback as soon as possible. And after I grade all quizzes on Friday, I'll be pulling the grades off MyLab statistics and then just updating your course score. So you can check your course score at any time. It sometimes gets updated a couple times a week, but usually on Friday after grading. Whatever your course score comes out to is going to be your official midterm grade for the course. So this is just going to be literally a halfway reporting point for us. And that's kind of cool news as well. At the end of Thursday's class, we're over the 50% mark. So congratulations, folks. About 8 more weeks to go. So those are the major things we're going to be doing. Midterm week is just reporting for us. And as far as chapter 7, chapter 10 goes, these are not going to make it on the next exam. I mean, we could put on the exam, but I feel like this is already big enough for material. And also, I like to make sure that you have a chance to actually do these problems as a quiz question, really spend some time in MyLab statistics, the reading and those kinds of things, asking questions about it. So the turnaround of doing this chapter this week and putting on exam is just too soon. This is going to be exam 3 material at this point. Well, any questions at the moment? Okay, we'll discuss the second exam a little bit more when we come back on Tuesday. And standard offer like we had on the last exam. Any questions you folks have relative to exam 2 material, whether it's old quizzes, anything off the sample exam versions 1 or 2, MyLab statistics problems, I'll be very happy to discuss them. So just let me know. I'll pretty much just open up the start of class for calling those kind of questions. We can spend as much or as little time as we need. And after we are done calling questions, we'll just go into anything we might have left off in chapter 7 or going to the next chapter 10. So exam 2 is going to be based off a chapter 3 question. And we didn't do a lot in chapter 3. We just looked into a two-way table. We computed some proportions and looked into a couple graphs. So it's a pretty targeted section. If you review the notes in chapter 3, that's about what the questions are going to look like. Chapter 4 is a little bit longer, but still a pretty targeted section as well, or chapter, I should say. For this one, you should know how to do a box plot, use the 1.5 IQR rule of thumb for plotting the outliers on your box plot as well, detecting them, and just making some quick summary comments based off the data once you have the box plot. There's a quiz based off that one, I believe. That one must have been quiz 4, or was it? Let me double check that before we lie about it. So what was quiz 4? Feels like a while ago already. Quiz 4 was, yeah, doing a box plot. So if you see your quiz 4 material, this is a pretty close question to what you can expect on a real exam. Exam number 2. And then next part, it's going to be a 4-question exam. Let me fix that real quick. There we go, almost. It's hard to get exactly sometimes. Next section for the 3rd question is going to be very similar to quiz 5, like we mentioned. That's using the calculator to come up with using normal CDF for a percentage or inverse norm to get a value on the horizontal axis relative to the questions there. And chapter 6, I'm going to write a brand new quiz to post right over here. My quiz for quiz 6 is going to be a highly similar question that you can expect on the chapter 6 as well. So I felt like on exam 1, as far as the quiz went, exam 1 material was kind of all over the place. The quizzes weren't as targeted to the real exam questions as I would have liked. But for exam 2, they're going to be a little bit closer, I would say. Looking over your quizzes will be a great way to study. Looking over either version of the sample exams will be a helpful way as well. And probably the biggest thing to mention about the exam is writing out your formula sheet for notes is probably the single most important thing to do as well. It's something you should do before you even start studying for the exam, and then reference it as you study the exam is the best way to use that material. You can have anything you want on it. It's both sides, front and back, and I won't be collecting them. So I encourage you to just file it away, pull them out when we're reviewing for the final exam, and it'll be an excellent resource. And as you use that resource on exam 2, you might want to put a little mark on the formulas and concepts that you actually used, because that way you can tell yourself, well, this information I put on my page of notes was fluff, but this other information, I actually needed it. I need to cite it and use it. That can be another helpful way to see that information. But that's my whole spiel of announcements. That took 6 minutes this time. That's a lot of talking. Any questions at all before we start off our chapter 7? Okay, so next class, we'll start with exam 2 topics. I might say just a little bit more about what's on the exam, but we kind of said it all today, and we'll call for questions. But just so we're not too far behind on the course, let's take a look into what's going on in chapter 7 next. Here's where we left off. Looking at graphs like again from before, we actually did a little bit of work on these notes, and we just looked into some calculator output. We'll revisit this as we look into the calculator output again. The big takeaway is we're going to write down equations in this format. The calculator is going to do all the heavy lifting of computing B naught, which the calculator also calls an A, we'll call a y-intercept. We'll compute B1, which we'll call the slope. We plotted something with an intercept and a slope as well by hand, but that was just for a kind of a warm-up, just to get a feel for how this information relates. So you don't have to plot lines perfectly. In fact, the scatter plots are going to be plotted for us on a real exam situation for, say, this would be exam 3 material. And if we ever have to plot a line, we would just freehand it. So let's do just that on these notes. The line that we're going to plot is going to be called the least squares regression line. So it has a gigantic name. The idea is we want to draw a line that gets as close to every single one of these points as feasibly possible. But now we need a notion for what we mean by close. Here's the mathematical idea. We're going to call it y hat. That deserves some explanation already. Y hat is just a way to say the predicted y value. So y hat is just a way to say we're not talking about the actual data values that we see here in the scatter plot. So the actual data values are these ordered pairs, x1, y1, x2, y2, and so on. They would come from a graph much like we saw in chapter 6. Let's open just a quick one for reference. So on this graph right here, the 0, 1 would be the x1 to y1, or if it's written in a horizontal way, the 318.1 degrees Celsius would be the x1, y1. So that's all these data values are referred to as. They're just written as actual ordered pairs, comma separated. So for example, this point right here, potentially this is x1, y1. And trying to get a line that's close to all of the points as feasibly possible, all at the same time, means we're trying to make this as small as possible. We want to minimize this thing right here. So let's plot out what the line would look like. The a plus bx is really just this right here, the formula for the equation of the line, where b refers to the slope, a refers to the y-intercept. And so if we were to just freehand a line, it might look about like this. So this is another sum like we've seen before. The summation notation says, take expressions that look like these and add them up. In its expanded form, it looks like this. y1, I forgot to close my parenthesis there, y1 would just be that dot right here next to my red dot. A plus b x1, well, x1 is this value right here, but the a plus b x1 is just referring to a plus bx. So this distance right here, we can rewrite it on the graph. It's a form of distance that we raise to a power 2, and it's that distance here. So it's a vertical distance from the height of the y1 value, here's y1, to the height of the actual predicted value, y hat. So there's where y hat would be. We square that distance. If we didn't square it, it's much like dealing with standard deviation. All of these would add up to identically 0 and be just not useful to us any longer. So we raise them to a power 2, much like with standard deviation. And just for a reminder of what that looked like, and that feels like a long time ago at this point, that was all the way back in section 2.5. We were taking y1 minus y hat and squaring it. Same idea right here, it's just a little bit more built up. There's two variables, y and x, so that's why it just looks a little bit more different. Other thing that's different is we're trying to make this as small as possible. So we take every one of these vertical line segments. I won't draw them all, but just for a quick reference, there's loads of them. We add all of these up, squaring these distances, and we get a total sum. This is asking for a lot. The least squares regression line makes that sum as small as possible. That sounds like a humongous mathematical task, but there's in fact just a really fast formula for doing all of this at once. Calculator has it programmed in, ready to go, and the formula is just this information down below. The least square regression line that minimizes this gigantic sum, all these vertical distances squared, will have slope given by correlation coefficient multiplied by standard deviation for the y variable divided by standard deviation for the x variable. That's a crazy formula. If you're curious about it, the reading talks a little bit on how it's derived. And then the y-intercept just by a slightly different formula. The sample mean minus the same b1 times the sample mean for the x data. This is mostly here just for our own reference for the sake of completion. So it doesn't seem as mysterious. There's an actual formula behind this. But we'll be taking advantage of the calculator in computing our least squares regression line. So I won't be asking you to use these formulas directly. Again, they're just here for the sake of completeness in the notes. So that's what the least squares regression line does. There's quite a lot going on here. Let me try to fix that. Guess that's a permanent feature of the notes. We'll leave those on there. Let me see if I can delete that. There we go. It's minimizing all those vertical line segments, but I just wanted to focus on just one. Another thing that's a little bit confusing or tricky about this topic is there's an actual name for every one of these things that we're listing out. There's going to be n of them if there's n pieces of data. The thing on the inside, excluding the power 2, is called E1, and it is a residual. Residual is kind of a weird statement, but it's just referring to the distance from what the line is predicting and from what the data actually gave us. So we're trying to sum the square of the residuals. And this is something that we would need to have for our formulas. So let's put this boxed out formula down below. We'll use this equation up here occasionally. Goes pretty nicely with the figure. So E is what we mean by a residual. It's found by taking the value that you observe. That would be the x1, y1 value that we see here, the actual data value in the dot plot, minus the predicted value. The predicted value is the y hat value. So we take y minus y hat, the observed minus the predicted, and that's what we mean by the residual. So that line that we were looking into just makes this sum of residuals as small as possible. And writing it out again, that vertical line, just that first one, is E1, the first residual. And that was just Y1 minus Y hat. Y1 was the observed value in the data value. Y hat is the predicted value coming out of the equation of the line. That's a lot of things to put together all at once. So we'll look into two examples on these. And let me know if you want extra practice after we finish these two examples. I'm not opposed to doing a third example, the same kind on these notes as well. Well, again, we're trying to fit a line to the data. The line is not meant to hit all the points. Sometimes it might hit one exactly. That was just a coincidence as I drew it. It's trying to minimize these things, y minus y hat, those vertical distances when we square them. And the calculator is going to help us actually build the equation for this line. Any questions about all that so far? Okay, this is what makes statistics kind of tough in a certain sense. We look at some pretty gnarly formulas, but it's mostly for the sake of conceptualizing what the calculator is doing. And now we're going to give it a try in the calculator and see how all this comes together. Let me put this down below. So this is about algae blooms, or algal blooms, I guess is a different way to say it. I'll just say algae blooms for just makes more sense in my head. So we're told, for the sake of this context, looks like biological data, algae blooms can have negative effects on an ecosystem by dominating its phytoplankton communities, so other critters in the water. We're told that this particular scientific name for algal bloom is a nuisance algae infesting many parts of Northern Europe. So if you ever hear something about algae blooms causing problems like off the coast of Florida or in Northern Europe, they might be talking about this one in particular or a very close relative to it. So they want to study this, see how it grows. And this is a research team now looking into this effort. Research team examined the relationship between the net growth rate and the number of these grazers. By the way, this turns out to be real data. I'm not sure why I didn't put the source on this one. So this is a real study that was done. So there's two things happening. This is the algae that we're concerned about, and this is something that eats the algae. And if we can look into how that relationship works, it could be a way of controlling the algae blooms. So they looked into the net growth rate of this algae, and these particular grazers, Daphnia magna is the scientific name for that one, they put the algae in a test tube and put the grazers inside the test tube and looked at how fast the algae grew. We're told a net growth rate was compared by computing the initial abundance of the algae, that scientific name, in the experiment with the negative value indicating a decrease in abundance. So the grazers are the animals that eat this algae. The growth rate down below is how fast it's growing, the more things we put into the test tube. And the data makes sense. If there is one grazer, there's a negative net growth rate, so the presence of this algae is shrinking. Put in two grazers, and it's shrinking a little bit faster, faster still 3, faster still 4. Pretty big jump, though, from 2 to 3. That's kind of interesting, but it's random data, so it's a bit messy. And these are the data values that we see here now as a dot plot. Well, that's the relationship so far. Instead of highlighting these as green and blue as we did before for the explanatory variable and the response variable, I'll be using color coding for the slope and y-intercept since that's the new concept. But this would be the x variable. This one would be the y variable, where the first one is the explanatory and the second variable is the response. We think the number of grazers are going to explain how the growth rate goes down. That seems intuitive enough. First thing it's going to ask us to do is calculate the least squares regression line, then plot the line on the scatter plot above. Now, like we mentioned, if you see this problem on a quiz, probably quiz number 8 or on exam 3, you're not meant to plot this line exactly. If you did something like this, that would be automatically for full credit. The only way you might miss points on this is if your line looks maybe something like that. This doesn't get close to the points at all. Or maybe if your line did something like this, if it's just kind of way off, only looking at 2 points, not the entire pattern with all the data, we could miss points. Another way we can miss points, but I don't think this has ever happened before, is this would not be the kind of line we're going for. This is just randomness in the data. We want the line to do something else. We want to minimize the least squares. We wanted to minimize the square of the residuals. So our best fitting line would look probably something more like this. Again, it doesn't have to be perfect. We've practiced plotting quite a few of them in chapter 6. So the instructions are kind of weird. I'd probably just plot the line first. Then we're going to make the calculator compute it for us. It's going to be a y hat equals, let's go to the calculator and get those values. First thing we have to do is just hit the stat key to bring in the data, hit enter right away, and delete the old data from last class. So up arrow and clear, again, turns out to be a major time saver, so I encourage you to take advantage of that. Hit up arrow when L1's selected, clear again to wipe those out. And if you have anything different, let me know. We can go through the steps of just restoring the view right here. You should be looking at a blank L1, L2. Then just import the data. I'll get quiet at this point, and we'll go from there. One word of warning, when you put in the negative values, be sure to use the negative sign down below here. Okay, it's kind of nice. This was a short one to import. Anyone need any additional time? Okay, now next thing we do is hit the stat key again immediately. We're moving over to the middle tab to calculate as if you're doing the mean and standard deviation, but we're going for a different option. Under the calculate tab, go all the way down to option 8. You can also just press the 8 key, but it's helpful to just actually see it the first few times, just to make sure you went to the right option. With option 8 highlighted, just hit enter several times. This screen should be just like when you're doing the scatter plot and getting the correlation coefficient out from before. So it should say L1, L2, everything else blank. If everything looks good, just spam the enter key at this point. And here's the stuff that we needed. All we need for this is just the first 3 parts. So just that. Let me try a better screenshot here. So there's our output. The line we build when it says the least squares regression line goes like this. Y hat equals the A value plus BX. So whatever the A is right here, we'll just directly drop it in. Y hat equals negative 0.85 minus 0.91 X. And we've got it, folks. That's going to be the equation of this line right here. We know from the first problem we practiced on these notes that this line is going down, and so the slope should be negative on this one. Let me make sure I match up my colors from earlier real quick here. This is not a good one to swap on. So our y-intercept I'm going to do as blue. The slope I'll do as green. So this whole thing, including the negative sign, is going to be the slope. And this part is going to be the y-intercept. Doesn't hurt to add an extra note here since we're learning this topic. So the first term they give you is the y-intercept. I'll write that as just y-int for short. And the second number given is the slope. So it did a pretty big computation. Lots of stuff had to be calculated to get to this point. But now we've got it. That's the equation of the least squares regression line. Any questions whatsoever, folks, on getting to this point?
Can I ask a question about the refresher on the what was that? The coalition, what?
Yeah, the correlation coefficient was this line right here.
Okay, that's what I thought. I just wanted to make sure.
Yeah, and it's really close to -1, which tells us this is an actually very strong relationship, strong linear, negative, or going down direction relationship for that correlation there. The minimum it could ever have been was -1.
That's strong.
Exactly. -1 would mean all the dots are directly on the line. So it's just a full-on linear pattern at that point. Other questions at the moment? Okay, this is the part of the course where it feels a lot different than chapter 5, section 5.4, but we're really doing the same kind of thing. In section 5.4, what we were doing was we took data. Where's my data? Let me get to a problem. We took data that gave us some summary values. We got a mean, standard deviation. We called those parameters. We started modeling a population. We started asking questions about what percent of the individuals in the population have more than some value or less than some value. Or we asked other targeted questions along the lines of what arsenic concentration describes the lowest 25% of the population, so on. That's essentially what we're now doing here with this line right here. Sure, it's not a normal curve, but what we're imagining is this line is going to model something else as well. We can use this to make predictions. We can predict maybe what would happen if we had, say, 5 grazers. We can't predict what would happen if there was, say, 10 grazers, because that's way, way outside of the data. But maybe we can make a prediction what would happen if there were 0 grazers whatsoever. So these data values that we got, they were just random. And if we were to repeat this experiment over and over and over again with 2 grazers, we're not going to get -2.2 over and over again. That was just a one-off on our experiment. We'll get something pretty close. That's the predicted value that we would say we should be expecting to find if we were to repeat this experiment over and over again. It should be about at that level. So it's in this way, this line is now saying something about what happens in this experiment under repeated conditions. We're making predictions based upon it. And that's why the y hat, that like we mentioned before, is referred to as the predicted value. So that's what all the next questions are kind of all about. We're going to interpret the y-intercept, interpret the slope, and part D is calculate the predicted net growth rate for 2 grazers. They'll just be plugging in a 2 into the model and getting the height right here on the graph. First, let's give a couple of interpretations for the intercept and the slope, and then we'll use the model to make it a predicted value for 2 grazers. These are the questions that get a little bit tricky. I think they're pretty tricky in MyLab statistics as well, because sometimes there's a pull-down menu where you can select the right option to complete a sentence. Other times it's multiple choice where you have to select the right, most correct sentence, looking for what could be wrong. So we'll go through these carefully. When it's talking about a y-intercept, they're talking about that value right there. Give a practical interpretation of the y-intercept. Sometimes the y-intercept makes sense, and you can give a good interpretation. And other times it makes no sense at all, doesn't even fit the problem. The best way you can tell for each one of these kinds of things is ask yourself for a y-intercept, does x equals 0 make sense? In some problems, it makes no sense at all. So it all depends on the context. And that's why it was helpful to just put this in when we first look into the data. The explanatory variable, which is the x variable, was the number of grazers. So at 0 grazers, yeah, that would make sense. We could run this experiment and get its sensible value. They just happen to not have. They always had a grazer inside the test tube eating the algae. So if it does make sense, like in this problem, we can make an interpretation. We'll say the y-intercept of negative 0.85 is the net growth rate when there are 0 grazers feeding on the algae. So that's what the interpretation would be for these data. The intercept is a value that's way off the chart here at 0. It intersects the y-axis somewhere out here at negative 0.85. And it's still a negative growth rate, but that's just because we put an algae in its unnatural environment inside a test tube. It's just slowly dying. It doesn't have any food. So we get a negative value. Well, we mentioned the context in this problem the moment we talked about the net growth rate itself, the moment we talked about the grazers feeding on the algae. These are the elements of the context. We're just talking about the data as we saw it here, essentially. Well, any questions about that so far, folks? Thinking about the y-intercept? Okay, just for a further visual, we might take this off the note so it doesn't look too distracting. But if this scale went out to, say, 0, that'd have been pretty far to the left out here. Then there would have been a y-axis going this way. And this would have been at the value, negative 0.85. So that's what we meant by a y-intercept. What if we went backwards outside the data? Not by very far, that's just one element to the left. We would have gotten to the negative 0.85. This was at negative 2.0. So the higher you go, the closer you're going to get to, shouldn't have put, well, yeah, that would have been 0 for the x-axis. This here would not have been 0 itself on the y-axis direction. So that's just another way to visualize that. So interpreting the y-intercept really just boils down to this. What happens when the explanatory variable goes down to a 0? Next thing we'll interpret is going to be the slope, which is that negative 0.91. I think that one's a trickier interpretation, so let's use some graphics as well when we go to interpret this next one. You know, it's kind of up to the individual on whether part B or part C is trickier. I think part B is trickier because you have to memorize this part. A y-intercept occurs only when the x variable goes to 0. Then you have to break it down into context of what was x in the first place to see if it even makes sense for x to be 0. Or next problem, it won't make sense, so we'll see the difference. But the slope, it has a definite process. Here's what we do when we deal with the slope. The slope is going to be negative 0.91, and you can always turn that into a fraction. One divides into that evenly, but there's definite units that goes with this slope. This is a change in the vertical direction, so it takes net growth rate. So negative 0.91 net growth rate. So your numerator is going to be, let's put this in the notes as well, the unit for the y variable. Should make that y look like a y. It's an important concept. Down below is going to be the unit for the x variable, and that unit in this problem was number of grazers. Number of grazers. So when it comes to interpreting these kind of problems, this is pretty much the setup. This is the work in getting it done to get the right interpretation. And it goes this way every single time. You'll put in the unit for the y variable, so that's going this way. Let's put a little y here as well, just for emphasis. That's always the numerator. And down below is the unit for the x variable. So down below, X variable is always in the horizontal direction. So that's our X. And now when it says give a practical interpretation like before, this is a really tough question because it feels so wide open, but there's one thing we're going for specifically. We'll see it in MyLab statistics. We'll definitely do a quiz on this one and make a good comments when we're coming up to exam 3. The practical interpretation of this has to also use the context, and this is how it's going to go. So I would write down for each additional razor. I'm thinking of a slope being rise over run. So we increase by 1 for each additional razor, go up to the numerator, the net growth rate. You'll either say increases or decreases. It depends on that negative sign, whether it's present or not. Because we have a negative sign in this problem, we'll say the net growth rate decreases. That's something we should highlight as well. That negative sign implies it decreases by 0.91. So that's the whole interpretation of the slope. We don't say a lot. This is just the setup. And we're just essentially saying this fraction in words. Let's actually visualize that though. We have a point right here at 2. If we add 1 additional grazer, we'd be moving over to 3. So we'd end up on this location. So this is the denominator moving up by 1 additional grazer. For each additional grazer, let's say here, 1 additional grazer. We said next, the net growth rate decreases by 0.91. And that's because you have to go down, kind of missed a little to make the point bigger. We had to go down to get to the next value on the predicted line. So this is decreasing by 0.91. And that was, let me see if I can fit that in there. Net growth. I'll just abbreviate it to net growth. I can't fit rate inside there. So add 1 additional grazer, that's going this way horizontally. The growth rate is this stuff vertically, and it went down by 0.91 upon rounding. Oh no, the calculator gave us 0.91. That was probably a rounded value actually. So that's the whole idea with interpreting the slope on this one. What happens if you increase by just 1 value in the denominator? The numerator will tell you exactly what happens to the response variable. And that's a lot of information all at once to put together. Any questions about this one so far?
So where you wrote in green right there for your slope,
Yeah,
that's kind of your formula for your interpretation.
exactly. No matter what's inside here, it would be the same exact idea. So if I said negative 0.91, maybe cubic inches for an engine, and down below here is maybe miles per gallon. I'm not sure if that makes sense, but something along those lines. I would drop in the same exact words up here in the same exact order. For each additional miles per gallon, the cubic size of the engine decreases by a certain amount.
Right. But on the exam, you'll give that to us in the scatter plot, right? Like the breakdowns.
This stuff right here?
Well, I mean, like the units.
Yeah, absolutely. So I'll always have the units grazers, the unit net growth rate will be written in on the scatter plot. It'll also be given in the data table here as well. So pretty much it'll be pretty similar to the quiz 6 question, except that we're only going up to saying, what is the correlation coefficient? Saying what's the response, what's the explanatory. On the quiz 6 question, I'm going to give a table just like this, scatter plot just like this as well. So we'll be used to kind of seeing it in that sort of format for both chapter 6 and 7. Other questions at the moment? Okay, so far parts B and C, they're pretty intense. They're all just about saying what the least squares regression model is doing. what the interpretations are for each one of those values. And let's copy this down again. For the next part, we're actually going to make a prediction. Calculate the predicted net growth rate for two grazers. So here's the original table. We need another thing. We need our predicted value. That's y hat, but the full equation for y hat is this whole thing. So these are the things that you'd be looking at for solving this problem. It's kind of big. Put it right there. There we go. When it says calculate the predicted net growth rate for two grazers, it's kind of a fun problem. This is all you do. We're past the intense stuff, and you go y hat equals negative 0.85 minus 0.91 times this value. X was the number of grazers, so whatever X is, they state, it just drops in right here. So this one is just a computation. We'll just drop this right into the calculator, get a number out. So negative 0.85, go minus 0.91 times 2. Value I got was negative 2.67. And we did it, folks. There is a predicted net growth rate of negative 2.67 every time we put in two grazers into this test tube with that particular algae. That's not what the experiment got. The experiment got this value, right where the red dot is. That's the actual data value when we plugged in two grazers. And we can look into the data table itself. On the data table, two grazers was a net growth rate of a negative 2.2. But that was just one experiment being ran. This is telling us if the linear model is a good model, run that experiment over and over again, maybe 10 times, maybe 100 times. Our values on average are going to get closer and closer to this value. And all it was is this point right here. Go to two grazers, drop a point. The height of that point is negative 2.67. So that's our predicted value y hat. So now, again, we're doing something like chapter 5. We know what to expect to happen every time this experiment is ran. Any questions at all, folks, getting that predicted value? Yeah. No, actually, on exam, if you gave me just this, I would consider that full credit, absolutely. And think of this as just a visual. That's actually more for how to work the formula in Part D, but this would be completely optional for sure. Yeah, thanks for mentioning that. Sometimes I throw in a bunch of stuff on there. It's hard to see what part is the actual required part for the exam question. Other questions at the moment? Okay, I feel like Part E is kind of the trickiest question of them all on these. It's the one that we mentioned requires a formula. When it says residual, we mean the distance from the real data value right here to the predicted one that we just computed. So we expect negative 2.67. Our actual value is up higher, so we're expecting a residual that's going to be positive. Here's what the residual would look like as a formula. It has the symbol E to go along with it. That's a weird symbol for residual. It's always going to be the observed value minus the predicted value. So when we say observed, just one more reminder, that's the value that we actually observed in the data itself. That's what the experiment gave us. So this is the observed value. But then we made a prediction. We said, what would happen on the long-term average if we kept on putting in two grazers? We predict a net growth rate of negative 2.67, and that is this value right here. This is the predicted value. So the residual is always in that specific order, whatever is observed minus whatever is predicted. As a formula, it's just y minus y hat. And we've actually calculated the y hat value. It's the negative 2.67. We have to go up and look up the y value from our original data table. So let's pause right here for a moment. In our actual data table, for two grazers, you know what? This is a good one to add as well as a screenshot because this is tricky just to know where we got the data. Let's just plug that down below here. Doesn't have to be that gigantic. So on the value y, the one that's right here on the plot is this value right here. So this is the y value we're going to use for the two grazers. Here's the two grazers coming up from the original question. So we're going to plug in negative 2.2 for y over here. There's always a minus, so now we have double negation because y hat was up here, negative 2.67. So that means finally, E for the residual is going to be, let's go take a look in the calculator, negative 2.2 minus negative 2.67. Here I just typed it into the calculator completely verbatim, but you might have just said this is negative times a negative. It's just going to be a plus overall. That could have saved a little bit of time in the calculator. But either way you put it in, you're going to get a residual of 0.47. It came out positive. The fact that the residual is positive right here just means our observed value is higher than what we would have predicted. If this dot was below, it would have came out negative. There's so much to say here. I think that's an important concept as well, so let's mention it. If E is positive, the observed value is above the regression line. This is turning into a long sentence. And it is below the regression line. I'll just say below the line when E is negative. Okay, so far this is the experience in chapter 7. It's pretty intense. So this is just our first problem taking a look at it. We'll have another problem we'll take a look into as well. And depending on how we feel about it, I'll ask you all after class. I'm not opposed to looking into a third problem just to get some additional practice. Well, the reading is pretty helpful as well because as you see how the notes have gone, there's a lot of things you can say here. There's a lot of comments I wrote in. It's kind of overwhelming. We won't put in as many comments on the next problem. We'll make it kind of a more clean attack of the whole method. But any last questions or comments on getting through this one? Yeah. This one right here.
I know you went to that.
Or you mean say this value right here?
Yeah.
Oh, gotcha. So you hit stat, go over to calc, and then it's option number 8 for linear regression. So if you hit enter there, let me just double check on the calculator again. It gives you the A value and the B value, and we just put it together in that way. It actually gives you the formula of how it goes together. It prints out A plus BX at the same time. So just substitute in those two pieces, and it gives you us the Y hat line.
Thank you.
Absolutely. Other questions at the moment? Okay, let's try this out all over again. So that's a lot of stuff to hold in your head. Best way to get good at this is practice a lot of problems. So this is our next run at it. So example 2. This is another real problem. This one actually has a citation, International Journal of Nursing Studies. It starts off by saying, the authors of the paper, Statistical Methods for Assessing Agreement Between Two Methods of Clinical Measurement, so it sounds important, compared two different instruments for measuring a person's ability to breathe out air. You know, we've looked into a study of that before. That was the FEV measurements we were talking about, the forced expiratory volume, I think it was called. This measurement is helpful in diagnosing various lung disorders. And the two instruments considered were a right peak flow meter. So they're telling us the names of the actual medical instruments now. I'm imagining this is a big device because there's also a mini right peak flow meter. Let's see if we can take a look at one of those. Sometimes when you're looking into a brand new problem, this is a pretty decent skill for statistics in its own sake. This context sometimes might seem really vague. So if this was an actual quiz problem, just look up the context, and it can help a lot with putting this all in your head. So this is the right peak flow meter. It's not that big. It looks like something you put in your hand. What happens if we look for a big one? Maybe they were big back in the day. Oh, there's a case for it. So I guess they're kind of big. So if they can come in a case, then they're pretty big medical devices. And apparently there's a mini one. This is maybe useful for maybe if you're being deployed somewhere, say Doctors Without Borders, something like that. You don't want a whole case for one device. You want to pack as many devices into as little space as possible. So micro devices could be useful, but they aren't guaranteed to be reliable. Here's what they did in this real study. 10 participated in the study, and for each person, airflow was measured once using the right meter. So that's in this column right here. And once using the mini right meter. So in this column right here, this is an identifier, not an actual variable. Notice the relationship though. This one came first, so we're thinking of this as the X variable, or the explanatory one. Like I mentioned before, I'm never going to mix that up on a real data table because it's just not good practice in the first place to put in these columns in different orders. Second variable is the Y variable, which is now the response variable. And so this is possibly the more reliable device, the full-fledged right peak meter. And then there's the micro device.
Backward.
Sorry, say again? Oh, you're right. The mini is this one, the smaller one. And then the full-fledged device is on the one on the right here. So let's see if this even makes sense. It really is the explanatory variable. I would hate to have that been backwards. That would have been me lying about how we're presenting the data. This is a lot of context already. Sometimes statistical problems get long, and this is one of them. Part A is another kind of like a book. Suppose that the right meter is considered to provide a better measure of airflow. These subjects were measured on both devices. And this is the more accurate one, we're being told. But the mini right meter is easier to transport and use. If the two types of meters produce different readings, but there's a strong relationship between the two readings, a high correlation coefficient, it would be possible to use a reading from the mini right meter to predict the reading from the larger right meter would have given. So yeah, they're saying that this might predict what these values could be. Maybe we can find a formula that says how we get these responses from just a mini right meter value that you have if you just had this one piece of data. So use the given data to find an equation to predict the right meter reading, the big device, from the mini right meter. So the little device, again, yeah, that's the little one. Thanks for mentioning that. I've got those backwards looking at the first time. So when it says find an equation to make that prediction, this just means find the least squares regression line. We're looking for y hat. So find y hat is all we need to do for this problem to get it started. Well, any questions about that so far? This one didn't come with a scatter plot, so we're just doing the best we can with what we have the data table. On a real exam question, like I mentioned, I'd probably pair both of them together, both the data table and a scatter plot. But to start this off, hit the stat key and enter. Clear out your variables in the usual way. And I'll get quiet as we add in 20 values, one for each column. Okay, I think I've got them in. Just another piece of advice doing this in the homework system, MyLab Statistics. Going slow is going fast, because if I mess one of these data values up, I could lose a lot of time on this, trying to figure out which one it was. Anyone need any additional time? Okay, next operation, once you have your data in, you're satisfied with it, hit stat, move over to calc, and if you know what you're doing because you've done it a bunch, just punch the number 8. But scroll down to be careful, make sure it says linear regression a plus bx, and that's the right operation. Spam the enter key as normal, and this is what we get. We have a plus bx, let's write that in just as kind of a structure, y equals a plus bx. I'll write that as a y hat to remind ourselves these are all going to be predicted values, not the actual values in the data. And so the equation is going to be for y hat, it said round to 2 decimal places, and so the first one rounds down. A is going to be 120.95. Then B is a positive, so let's go plus. To 2 places, we can round that one up to 0.75. And then multiply it by x. So let me double check my color coding one more time. So slope is green. The slope in this problem is the 0.75. And the y-intercept is 120.95. So this line does a good job. Well, let's look into that. Notice the correlation coefficient on this one is R equals 0.93. That means we have a very strong linear relationship. Is it linear? That's going to depend on what the scatter plot looks like, right? This next operation is really just for the sake of the homework, really in chapter 6. If this is a real relationship, we should be able to see it in the scatter plot. And so if you want to look into the scatter plot, hit zoom, go to, I forget the option, zoom stat, option number 9. Hit enter there, and it doesn't look too bad. It looks a little bit flat on the left end, so I think it might be debatable what's going on the left end. Some people might said nonlinear because maybe you could curve that a little bit better. But if you want to look into the actual scatter plot, there it is. Let's save that just in case we need it for something.
MyLab Statistics would say that's a straight or linear.
Would they for a lot of those
I think
options?
so, from what I see.
Yeah. Well, going by this problem, it seems to make sense, or else it would have been a bad fit for this one as well. And trying to put a line through it, doesn't look too bad as a line, right? It's just tough as a problem where other people might have saw it in a different way like that. It becomes really subjective. And that's why there's a lot of tries in MyLab Statistics, because it just feels unfair if you saw it one way versus another. Yeah, go ahead. Yeah, absolutely. So if you're back, say, here, we've got the data calculated, and back over here on option 8, where you had this data calculated. The next thing to get the scatter plot would be go to this zoom right here at the very top. Then the option that we want down below is the zoom stat button, number 9. Absolutely. That's a good one to remind ourselves on. This can save a little bit of time on MyLab Statistics. So let me put this in on the notes as well. So you click on that button and then on zoom stat. Okay, let's put that down below. Thanks for asking about that. I think that's a good addition to the notes. Okay, well, we have a pretty good correlation. We have a model. Looks like a pretty nice linear line. Again, sometimes these are debatable. MyLab Statistics only gives one answer to these kinds of things, making it sometimes frustrating. And here's what part B is asking. What would you predict for the right meter reading, the big device, for a person whose mini right meter reading was 500? When they say the mini right meter reading was 500, that's this value, X. That's these values right here. There's no there is a 500. There is one 500 and it came out as 516, but that's the actual observed value. We're asking for a predicted value. So we want a y hat value coming from the model itself. So it's tempting to put in 476. It's just looking at it, but that's the data. That was just one random observation. So let's compute. For this problem, it's y hat equals 120.95 plus 0.75 times 500. So this will give us the amount that the official larger device, the more standard one, would have given. That's kind of cool in a way. We can, if there's a strong correlation, use a less reliable device, but translate what we would have potentially gotten with the more standard device. So let me clear off this annotation first. There we go. In my calculator, I've got 120.95 plus 0.75 times 500. So this is the value that we would have expected. Notice on the observed value was 476, but the value we would predict is 495.95. So everyone reading about a 500, this is their official value by our model, 495.95. You know, one thing that's weird about this problem is I have no idea what the unit is for this. So that's something we probably would have to research if we're curious. Any questions at all, folks, getting that predicted value? Okay, well, we've got it, the 495.95. Next thing we're going to do is calculate the residual. How far off is the prediction from what we actually see in the data? So this is the one that requires a formula, which goes E equals Y minus Y hat. So observed minus predicted. The observed value is still targeting relative to 500. Let me change that highlighting up here. So when the mini right meter was 500, we're on this line right here. And this is Y, the observed value. 495.95 is the predicted value. So we'll calculate 476 minus 495.95. And here's what we get in the calculator. 476 minus 495.95, giving us a negative 19.95. We get a negative residual once again. And that time, or excuse me, this is the first time for a negative residual. The residual is negative because the observed value is less than the value that we actually predicted here. So that means I don't actually have a scale here, tragically. The highest is 6, that'd be hard to find. But if we're looking into that value, actually, let's see if we can find it. Let me go back to Zoom 9. If you hit trace here, you can move across the values. Let's find the 500 one. There it is. It was this one right here. So that line. So our value, right where the red dot is, even on the line that I drew, which is imperfect, this is just freehanding the best fitting line, it is below the line, just barely, but it does come out below. Well, any questions at all, folks, on computing the residual? Okay, so these are the main kind of computations that we'd be doing on each one of these problems. The next one is doing another run through interpreting both the slope and the intercept. So let me carry down the model one more time. Let's maybe just park it over here where it's just kind of out of the way. So we want to give a practical interpretation of the slope and a practical interpretation for the y-intercept. You know, let's actually go a little bit out of order this time because we're running a little bit shy on time. And I think part E is the more interesting one. I wish I switched the order here. So let's do something rare and do part E first. Does it make sense to interpret the y-intercept of the least squares regression line? So the y-intercept is this value right here. What would you folks say to this? Would it make sense to interpret that value there? These are tricky questions, keep in mind. When we think about this question, does it make sense to interpret it? We need to be thinking of what are the variables? What is the underlying context? And the other thing to think about when it comes to y-intercept is a y-intercept always occurs when x equals 0. But what was x? We go to the top of the data. X is the mini right meter reading, which is a measure of airflow. So going back to this, x equals 0, would that make sense? What's that?
It never happened.
Exactly. Imagine it did happen. This is a person who is not breathing, right? This is a medical emergency. If you put a measurement device and it comes out as 0, the person's lips are probably purple or something like that. You should be doing CPR and not answering this question. So this doesn't make any sense at all in this context. 0 means a person is probably dead or struggling or just being weird and not doing the experiment the way they should be doing. They're supposed to exhale into the device. So absolutely, the value at x equals 0, the measurement reading of 120.95, it's important for the model, but it has no bearing on reality for this experiment. So we'll say here, since x equals 0 means a mini right meter reading of 0, which means the subject is not breathing, it does not make sense to interpret this value. It has no meaning whatsoever. So good call on that one. This one is a nonsensical value. And on these kind of problems, it's kind of a pot shot. Half the time they make sense. Other half the time they have just no bearing on reality whatsoever. Does that make sense to folks on what went wrong with this one? Okay, there's another idea that we'll come back to and discuss as well that makes x equals 0 kind of nonsensical. If you look at the original data and you never even thought about the context, none of the values are 0 whatsoever. This model only works for values in this range. It has to be above 346, below 658. Sure, we can make a prediction of maybe about 670, maybe even 700. But if you plug 1,000 into this, this is someone with like really crazy lung strength, a world-class athlete. This model breaks apart. That's called extrapolation if you go way, way outside the model. And 0 is extremely outside this model. No data is ever in that range whatsoever. So 2 reasons this doesn't make sense. 0 means the person's not breathing. They're either in a medical emergency or just being weird when you're trying to run an experiment. And it's extrapolating. No one's even close to 0 on this model when we looked into the data. But we'll come back to finding the slope, doing a little bit more predictions and residual kind of work. And I'll leave it up to the class at this point. Do you folks feel like we should look into an additional example on this, an example 3? Any volunteers for strong feelings one way or another?
I'm down for it.
Okay, I'll prepare another example like this, and we'll make sure to take a look into that example before chapter 10. And then another reminder, before we do anything at all, when we come back Thursday, we'll call for questions on exam 2. So if you have burning questions you want to discuss right away, that'll be our first order of business. But have a great night, folks. We'll come back to this eventually after we get through those other things we mentioned. Yeah. Yeah, absolutely. Did you have one in particular you want to take a look into? Yeah. Absolutely. Last time we did this, we just decided there was no questions, so we didn't at all. So I'm gonna put in here reminder two. Okay, so if no one has any questions at all right away, I'll pick one myself and definitely put it on there. And then we can go from there after that. So I'm gonna write here as a reminder, definitely do at least one question. Thanks for mentioning that. I think I need more context to remind myself what this is about. Definitely do at least one question for the exam to review. Thanks, you too.